Now with the mean value theorem for derivatives, what we're looking at, first of all, there are three conditions we have to satisfy. If we have a function, we need to know, first of all, that is continuous. Secondly, that we have a closed interval, so we have definite endpoints and we're following all along there. And third, that it is differentiable at every part inside of that closed interval. It can be open ends though. They don't have to be differentiable on the endpoints, but everywhere from there it needs to have a derivative. That's guaranteeing basically that we have a smooth curve, there's no corners or anything. If we satisfy those three conditions, then what we know is if we connect those endpoints as a secant line, so basically taking an average slope here, we'll take an average slope, then there's somewhere on that curve between them where we have a point where we're actually parallel to that average slope, to the secant there. So our derivative somewhere, there's some point where it will be equal to our average slope. Now there might be more than one point, but it guarantees at least one. Okay, so here's another example here from A to B. I connect my secant line. Somewhere on this curve, we have a derivative that's parallel to that. So for this function here, we have x squared, and we want to show first of all that it satisfies that we have a closed interval. So first of all, for x squared, we know that it is continuous. We do have a closed interval. We're going from 0 to 2. And is it differentiable on 0 to 2? So we can take a derivative of this. We know that f prime of x would be equal to 2x, so it would be differentiable everywhere on that interval. So yes, it does satisfy the mean value theorem. So we do want to check all three of those things, making sure, again, continuous, closed interval, and differentiable. Then we plug in the values that we have. First of all, we plug into the original function to think about the endpoint. So I got f of 0, f of 2, and so my average slope over that interval, we're just checking those are equal. So my average slope over that would be 4 over 2, which is 2. And what we're looking for now is they want to know a solution to this equation. They want to know what this point C is, what x value will satisfy this. Now sometimes there could be more than one, but basically we're setting our derivative, plugging in the value C for this, because we don't know what x is going to work. We set it equal to our average slope of the endpoints, and then we'll find that at a value of 1, that we'll actually have a slope parallel to our secant line. Okay, so in these two problems we want to look at why these things would fail. Now we see here that there's a corner here, which is telling us that we don't satisfy the second part of this. So first of all, it is continuous, and it is a closed interval going from, well, they asked about -1 to 1, so we can plug in any of those values here. But our third condition, that it is differentiable. We can see here a corner. We can also show that maybe by looking at what this actually means. Notice this is actually the square root of x plus 1, which we would have to represent as a piecewise function in order to take the derivative of that. But if we know what this value is here, we can show that that would have to be different. If we look at f prime of x, then there's going to be a piecewise function where on the one side we have a slope of -1, and on the other side we have a slope of 1. And so that is not continuous. It doesn't fit the mean value theorem. Okay, on the other one, we don't even have to go that far. You can see in the graph the discontinuity here, but the first thing we can check, if we're checking for continuity, is just plug that 1 in to each side here. On the one side I would have 1 plus 3, which gives me 4. On the other side, 1 plus 1 equals 2. So since we have different values there in that discontinuity, we don't even have to check the other part. We know that this does not satisfy the mean value theorem. Okay, in this problem we want to find the tangent. So here are our endpoints at -1 and 1. If we take the slope between those, we can see that that is the average slope there will be equal to 0, going from -1 to 1. Now we want to find where our derivative is equal to that. So we need to look at f prime of x. Now first of all, notice again, this is continuous. We have a closed interval, and now we're going to see what the derivative is. We could think of this as 1 minus x squared to the 1/2, which is going to be equal to a -x over the square root of 1 minus x squared. And then we're next going to set that equal to our slope. So we know our slope that we want is 0, so we want to know where our derivative is equal to 0. And so that's going to happen when x is equal to 0. Now notice that there are points where this is not continuous. We would have a problem at x equals 1 or negative 1. Remember, for our mean value theorem, it's okay for the endpoints to not be differentiable as long as it's differentiable on the open interval. Now our tangent line at this point, this is looking at x is equal to 0. That's telling us where the tangent line is. And we could go a little bit further and notice that tangent line is the line y equals 1. One way that this mean value theorem can be interpreted practically is if we have an example where a car is accelerating. So we're starting from a speed of 0, we accelerate over that time, and we look at the average speed over this as the secant line, basically the slope between the endpoints, giving us an average speed of 44 feet per second, or 30 miles per hour. Now what the mean value theorem is telling us is that somewhere, even though we're starting out slowly and accelerating, going faster at the end, there has to be some point on that interval where we're actually going exactly 30 miles per hour, or graphically where we have parallel lines.